Salam and peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Remember the language we are learning together? There is one field called phi, spelled Phi. Phi is the holophase, a cyclic rhythm defined at every point in the universe. Its first derivatives give three simultaneous echoes: time, which we call omega, spelled Omega, space, which we call k, and motion, which we call v, built from both omega and k. Above them, higher derivatives form a branching tree that in principle goes on forever. Every law of nature is a pattern in this tree of derivatives of phi. Today, we zoom into just one branch of that tree. In part 11, we met phi as the silent root of the language. In part 12, we listened to omega as the pulse of time. In part 13, we felt K as the weave of space. In part 14, we joined time and space into a single combined change, which we called dphi, the way phi responds as you move through both time and space together. In part 15, we learned to write the patterns, and we saw V as the motion that keeps you aligned with a phase feature instead of being cut by it. Now, in part 16 of episode 6, we climb one step higher in the master tree. We leave the simple first changes and we begin to explore the changes of the changes. This is where the language of holophase develops its accents, its curving, its shading. If first derivatives tell you the basic rhythm and weave of reality, second derivatives tell you how that rhythm bends, sharpens, softens, and focuses. To make this simple, I want you to imagine that the holophase language is like handwriting. The first derivatives tell you the direction and speed of your pen as you write each stroke. The second derivatives tell you how the stroke curves, where you press harder, where you lighten up, where the letters lean or straighten. Without those accents, handwriting would be a collection of straight lines, all the same. With them, your script becomes alive. In the holophase language tree, the key second derivatives that we will focus on in this part are three: alpha, which lives on top of omega, G, which lives on top of K, and what we can call the convergence of K, which tells us where the spatial patterns focus or spread. I will say more about each of them in simple words. For the audio listener, you can picture alpha as how the ticking rate changes, G as how the slope of phase bends, and convergence as how the threads of the pattern come together or flow apart. Let us begin with alpha. Omega, as you remember, is the local tick rate of phi in time. It tells you how fast the phase is turning at each point. Alpha sits just above omega in the temporal branch. Alpha asks a new question. Is the local tick rate itself speeding up or slowing down? In other words, alpha is the change of omega in time. You have felt alpha in your life thousands of times, even if you did not give it a name. When you sit in a car and the driver presses the accelerator gently, you feel your body pressed back into the seat. The speed of the car is increasing. Speed by itself is like omega. It is a rate. The feeling of being pushed is linked to the change of that rate. That change is what physicists call acceleration. In the holophase language, alpha is the acceleration of the local temporal rhythm. Let us describe this for your ear, without writing any equations. Imagine that you are listening to a metronome clicking on a table. If the clicks come at exactly 1 per second, that constant cadence is like a fixed omega. Now imagine that click by click, the metronome speeds up. First, one click every second, then slightly faster, then faster and faster, until it becomes a rapid buzzing. The way the interval between clicks shrinks is alpha. If the clicks slow down, alpha is negative. If the clicks speed up, alpha is positive. Omega tells you the rate right now. Alpha tells you how that rate is changing. This is not just a musical trick. In the holophase picture, alpha is defined at every point in the universe, just like omega. It tells you how the local tick rate of phi is bending in time. Some regions might be in a steady rhythm, with alpha close to zero. Other regions might be winding up or winding down, with alpha strongly positive or strongly negative. Why does this matter? Because a changing tick rate can have profound physical effects. When the local rhythm speeds up or slows down, it can stretch or squeeze patterns that are locked to it. It can focus waves or spread them. It can stabilize structures or make them unstable. In ordinary physics, some of this appears as time-dependent forces, or as fields that change in time. In holophase, alpha is one of the clean letters that make this behavior visible in the language. Here is a simple, everyday analogy. Think of a treadmill in a gym. You are standing on the belt. The belt is moving and you are walking to stay in place. At first, the belt speed is constant. You find a steady rhythm. Now imagine that the treadmill begins to slowly speed up without telling you. At each moment, the speed is a little higher than before. You feel that you must take slightly quicker steps to keep up. That gradual increase in belt speed is like alpha being positive. The local motion rhythm is accelerating. If instead the treadmill slowly slows down, you may feel that your legs are overstepping and you need to relax. That is alpha being negative. The rhythm is decelerating. Now, what does Holophase say and how can we test it? Holophase claims that alpha is not just a convenient way of speaking. It is a core part of how the phase field itself changes, and it should appear in many places in physics once we rewrite those situations in the holophase language. For example, in the presence of changing gravitational fields, or varying electromagnetic backgrounds, or rapidly modulated media, Holophase predicts that local alpha values will leave specific fingerprints on the behavior of clocks, resonators, and waves. If precision experiments ever show patterns that cannot be reconciled with any reasonable alpha landscape, that would be a serious challenge to the theory. On the other hand, if diverse experiments can be described using a coherent alpha field, that strengthens the case that alpha is a real letter of nature's language, not just a poet's invention. Let us now turn from time to space, from alpha to G. When we spoke about K in part 13, we said that K tells you how quickly phi changes across space. If you imagine the phase as a kind of landscape, K is the slope. Where K is large, the slope is steep. Where K is small, the slope is gentle. G, which I will simply call the curvature of the phase landscape, sits one step above K. While K asks how steep is the hill here, G asks how fast is the slope itself changing as I move. To feel this, imagine you're walking up a hill. At first, the slope is gentle. You're not working very hard. As you go on, the slope becomes steeper. Your legs feel the extra effort. Then, near the top, the slope may ease again. Your body is very good at detecting not just how steep is it right now, but is it getting steeper or flatter as I go. That sense of the slope changing is curvature. G is the holophase letter that measures curvature in the phase landscape. A straight, flat road has zero curvature. A road that bends steadily in a circle has one kind of curvature. A roller coaster that bends and twists with changing slope and direction has a rich pattern of curvature. In the same way, a phi field that changes linearly across space has little or no curvature. Its slope is constant. A phi field that bends, bulges, or twists has non-zero G. Wherever G is large, small changes in position produce big changes in slope. Why is that important? Because curvature guides flows. In many physical systems, the paths that waves or particles follow are deeply influenced by curvature. Light bends when it passes through lenses because the medium's properties change in a curved way across space. Rivers carve curved paths through landscapes because of how the ground's slope and curvature combine. Even in general relativity, the deflection of light by massive objects is framed as motion through curved spacetime. In Holophase, G is a way of talking about such curvature entirely in the language of phi, without introducing separate geometric ingredients by hand. Let us picture it more concretely. Imagine you are rolling a ball down a surface. If the surface is a straight slope, the ball accelerates in a simple way. If the surface has a curved valley, like a bowl, the ball may spiral, oscillate, or come to rest at a central point. The shape of its path is determined by the curvature of the surface. Now replace the physical surface by the abstract phase landscape of phi. G tells you where that landscape has bowls, ridges, and saddles. Those features then influence how phase patterns move and interact. Holophase says that many things we usually describe as forces can instead be seen as the effect of G on the motion echo of V. Instead of saying a force pulls this object, we can say this object is following natural patterns in a curved phase landscape. This is not merely a philosophical preference. It leads to specific mathematical forms for how V changes when G has certain structures, and those can be tested. If those forms never match reality, the holophase proposal fails. Now we come to the third second derivative in our trio, the convergence of K, which, for the listener, you can simply remember as how the threads of the spatial pattern gather or spread. K, as we said, is the local weave of space, the way phi changes as you move in different directions. If you draw K as little arrows or threads across a region, some areas might show arrows that seem to flow inwards, like water running into a drain. Other areas might show arrows that flow outwards, like water spreading from a spring. The convergence of K is a number that captures that inwardness or outwardness. Where the convergence is positive, arrows tend to point inward and patterns concentrate. Where it is negative, arrows tend to point outward and patterns dilute. To feel this, think about weather maps. When meteorologists draw arrows to show wind, they often pay attention to whether winds are converging into a region or diverging out of it. Converging winds can lead to rising air and cloud formation. Diverging winds can lead to sinking air and clear skies. The convergence of the wind field is a very practical quantity in weather prediction. In holophase, the convergence of K plays a similar role for the phase field. It tells us where phase patterns will tend to focus and where they will tend to spread. Here is another visual. Imagine drawing many lines on a sheet of paper to represent directions of K. In some areas, the lines seem to crowd together, forming dense bundles. In others, they fan out. The convergence is a way of turning that picture into a number at each point, saying, here the pattern is gathering, or here it is dispersing. This number then enters into the holophase equations that predict how waves and defects will behave. Regions of strong convergence can act like lenses or attractors. Regions of strong divergence can act like sources or repellers. Once again, falsifiability demands that this not remain a metaphor. If holophase says that the convergence of K controls the focusing of certain wave patterns, we can set up experiments with waves in water, sound in air, or light in special media, and check if those patterns appear where and how the theory predicts. If they do not, we must either revise the theory or abandon that interpretation. If they do, we gain confidence that the language letter we are using actually corresponds to something real. We can now step back and see what we have done in this part. We started with first derivatives, the basic rhythms. Omega for time, K for space, d phi for combined change, V for motion. In this part, We climb from those rhythms to their accents and bends. Alpha, the change of omega in time, G, the curvature of the phase landscape, and the convergence of K, the focusing and spreading of spatial weave. All three are examples of second derivatives. They ask, how does the change itself change? There is a simple human way to name this level. First derivatives are about what is happening right now. Second derivatives are about how is what is happening right now itself evolving. In our emotional life, we feel this too. We do not only feel happiness or sadness, we feel whether happiness is rising or falling, whether sadness is deepening or easing. That change of the change is often what we actually react to. In Holophase, the same pattern appears in the language of phi. At the most basic level, phi, omega, k, d phi, and v give a snapshot of what the phase is doing right now. At the next level, alpha, g, and convergence tell us how that snapshot is bending into the future. They carry the seeds of stability and instability, of focusing and defocusing, of speeding up and slowing down. For the audio listener, I invite you to anchor each of these letters in one clear image. For alpha, picture a metronome that is not steady but is gradually speeding up or slowing down. For G, picture a hill where the slope itself is changing, or a roller coaster track that bends more sharply in some sections than others. For convergence, picture arrows on a map, flowing into a drain or fanning out from a source. These three images are enough for now. Later, when you encounter the same symbols in the written Holophase codex on Zenodo, you will remember that behind the dry notation live these very simple ideas. Before we finish, I want to slow down and invite you into three small experiments of awareness that you can do in daily life to feel these second derivatives in your own body. First, an experiment for alpha. The next time you climb a flight of stairs, pay attention not only to how hard it feels, but to whether the effort is increasing or decreasing. At the bottom, you start fresh. As you climb, there is a moment when your breathing begins to quicken. Then, if you keep climbing, it may stabilize at a steady rhythm. In the very first steps, your personal omega, your internal tick rate, is changing quickly. That is alpha. Later, when you reach a steady pace, alpha drops towards zero. You are no longer speeding up or slowing down, you are simply keeping time. Holophase says that, beneath this subjective feeling, there is an objective field alpha, defined across your body and the stairs, describing how the local phase cadence changes. If, one day, we build instruments delicate enough, we should be able to track such changes in the phase language directly, and see the same patterns that your lungs and muscles already feel. Second, an experiment for curvature G. Find a road or a path that is not straight. Perhaps there is a gentle bend near your home. Walk it slowly. Notice how your feet and your eyes anticipate the turn. Now imagine that the road designers had made the turn sharper in the middle, like a sudden kink. Your body would sense that something is different, even before you look down. The way your step adjusts, the way your balance shifts, reflects sensitivity not just to the direction of the path, but to the way that direction is changing. That is curvature in action. In a holophase universe, any object moving through a curved phase landscape feels an analog of this guidance. Not because a mysterious external force acts on it, but because following the phase patterns naturally leads it along certain routes. Third, an experiment for convergence. Picture a busy city square with many people walking. Sometimes the flow of people converges towards a single exit, like a doorway to a train station. At other times, the flow diverges as people spill out of a train and spread into many side streets. If you stand still and just watch, you can almost see an invisible field of arrows describing the movement of the crowd. Where the crowd converges, you might feel a sense of compression, a narrowing of space. Where it diverges, you feel an opening. The convergence of K is a precise way of describing such patterns for phi. If holophase is correct, the focusing of light in a lens, or of sound in a concert hall, or of waves on a shoreline, all share a deep kinship with the flow of people in that square. They are all examples of patterns converging and diverging in a field. These simple exercises are not proofs. They do not replace experiments with lasers, atoms, and careful measuring devices. But they help your intuition grow in the right direction, so that when you later hear about alpha, G, and convergence in a technical context, they feel like old friends rather than foreign symbols. Let us talk a little more directly about falsifiability, because it sits at the heart of this entire audio journey. In the written Holophase Codex, which you can find on Zenodo, alpha, G, and the convergence of K are not introduced as loose metaphors. They enter into equations that are designed to recover known physics in familiar regimes. For example, certain combinations of G and convergence are constructed so that when you ignore the deeper phase structure and look only at observable patterns, you recover the same predictions that standard theories make for how light bends near massive objects, or how waves focus in graded media. This is the first test. Holophase must not break what already works. If it fails even there, it does not deserve attention. But the second, more interesting test comes when we ask questions that standard theories leave awkward or unanswered. For instance, what happens in regimes where phase defects, curvature, and rapid temporal changes are all important at once? What happens near strong topological structures, where phi winds around many times? In such cases, the holophase equations often produce clear statements about how alpha, G, and convergence should be tied together. They may imply, for example, that when curvature has a certain pattern, convergence cannot be arbitrary, or that when alpha oscillates in a specific way, certain kinds of wave packets must respond with a matching change in their motion echo v. These are the kinds of statements that can guide experimental design. A laboratory could create a controlled medium where the effective phase landscape can be tuned, and then test whether wave packets actually move in the ways holophase predicts. If they do, we gain evidence that the language captures something real about how nature organizes change. If they do not, then, however beautiful the story, we must admit that the language is incomplete or wrong. There is also an important conceptual falsification at stake. Holophase claims that we do not need to introduce separate, unrelated entities like force fields, geometric backgrounds, and time-dependent potentials as basic ingredients. Instead, it claims that alpha, G, and convergence, all derived from one phase field phi, are sufficient to describe such effects. If, in practice, we always find that we must smuggle in extra, independent ingredients that have no clean expression in terms of phi and its derivatives, then the dream of a truly unified phase language would be in trouble. The universe would be telling us, kindly but firmly, that it does not speak the way we imagined. For the listener, I want you to feel the humility and the ambition of this program at the same time. The ambition is obvious: to describe reality as one coherent language built from a single field and its derivatives. The humility lies in the way we hold this as a proposal, not a dogma. At every step we say, here is how the story could be written. Now let us see if the world agrees. You are not a passive observer of this process. Even as a non-scientist, you can participate by carrying the images of alpha, G, and convergence into your own way of seeing. When you watch a bird swoop and curve, you can wonder how its path might look in a phase landscape. When you feel a car accelerate, you can imagine alpha fields pulsing through the metal and air. When you look at sunlight focusing through a glass of water onto a table, creating bright ripples, you can think of convergence at work. In this way, your everyday perception becomes a kind of informal holophase laboratory. One day, perhaps, children will learn this language in school, as naturally as they now learn about forces, tallies, and momentum. They will draw not only arrows for velocity and acceleration, but also simple sketches of phase landscapes, curvatures, and convergences. They will learn to see the world as a tapestry woven from patterns of change and change of change. If that day comes, it will be because theories like holophase have earned their place through both beauty and honest confrontation with data. Until then, our task in this audio journey is to build the mental scaffolding. We are walking slowly up the master tree, making sure that each branch we touch is clear, intuitive, and open to testing. Phi, omega, K, D phi, V, and now alpha, G, and convergence. These are the early letters and accents of the cosmic script. In future parts, we will add more grammar, such as topology, waves, and tallies of activity. But every new layer will grow from the foundations we are laying now. So as you leave this part and return to your life, notice when your own inner rhythms speed up or slow down. That is a hint of alpha. Notice when your paths through the world bend or straighten. That is a hint of curvature, G. Notice where patterns of motion around you gather or disperse. That is a hint of convergence. Let these observations be gentle reminders that beneath the surface of things, there may be a single, continuous phase field, phi, writing the story of existence with these very letters. In doing so, you quietly rehearse the new alphabet of reality we are unveiling together here.